All right, this video is for APCalculusBC and is for section 1-2 on using functions as mathematical models. Mostly what we're going to do in calculus is deal with functions, but for that to be useful in everyday life or physics or engineering or something like that, business, we have to have the functions match something or represent something in the real world. And it helps to know just in general how functions behave so we can do a good job of matching a particular function to a situation. So we're going to just look at different things to know about the general shapes and behaviors of functions here. First is we need to be able to agree on the names of different functional shapes. So let's review the main ones here. A linear function has the form of a line. And it's, for example, y equals 2x plus 5. So if you have something where you have y and x has no power, it's just x, and there's a constant term maybe, but there's a term with an x. Or even it could just be y equals 5. You can, if you have x is either present only to the first power or not present and constant, then you have a linear function. In general, they have the form y equals mx plus b. There's other forms too, like point slope form. Y minus y0 is mx minus x0, where x0, y0 is any point on that, right? You can also have special cases like y equals 5. That's a horizontal line where we have all the y's, which are 5, or x equals 2 is all the places where x is 2. So this is a vertical line. This is a horizontal line. Right, so you should be familiar with various ways to write lines. All right, let's see. Power functions. Power functions are something where we're taking the variable and raising it to a power. Could be an integer, could be a fractional power. If it's an integer, like we have x cubed, something like that, or x to the fourth, x cubed, x squared, then it's called a polynomial specifically, okay? And actually a polynomial is more specifically can have multiple terms, like 3x to the fourth minus x cubed plus 4x squared, etc., something like that, okay? To qualify as a polynomial, the power function has to use only integer powers, including potentially x to the 1. And you can even think of the constant as having an x, because that's like x to the 0 power, which is just a 1. So you only have integer powers of x for a polynomial, okay? And then whatever the highest polynomial power is, that's called the degree of the polynomial. Okay, but power can also be other things, x to, say, 1.8, something like that. That's still considered a power function. Okay, a rational function is specifically something that has the form of a ratio or a fraction. So think of it as a function that is in the form of a fraction, and it's specifically something that has a polynomial over a polynomial. So there's a numerator polynomial and a denominator polynomial. If you have something in fractional form, but the top or the bottom is not a polynomial, like this right here, which has x, the square root of x, that would be the equivalent of x to the 1/2 power. That means that technically the top is not a polynomial because that's not an integer power. So instead of calling it a rational function, we call it an algebraic function. Okay, trigonometric functions, they involve trig functions, sines, cosines, tangents, things like that. An exponential function has the variable in the exponent spot. So just to be clear, if I have x to the 5th, that's called a power function. If I have 5 to the x, that's called an exponential function. So what makes this an exponential function is the variable is in the exponent spot. And then a logarithmic function involves a logarithm. Sometimes you'll see the word transcendental functions. So transcendental just means that it transcends algebra. And that includes anything with trig functions, inverse trig functions, exponentials, or logs. All right. So some names. More importantly is to know the basic shapes of these functions. So we know that for polynomials or power functions where x is x to the n, if we're talking about integer powers, so we have this is x to the first power, x to the second power. Oh, they're written here. If we have x to the first power, x to the second power, third power, fourth power, so on. So up here above the line, if we're talking about polynomial terms, then the all the ones that are odd have the basic idea that they go down on one side and up on the other, down on one side, up on the other, down on one side, up on the other. The ones that are even powers, like 2, 4, 6, they go up on both sides, or they go down on both sides. So if you have like y is x squared, that goes up on both sides as it makes that U shape. If you multiply that highest order term by a negative, like negative x squared, then it flips everything upside down and it goes down. Same thing with odd powers. If you have, let's say y equals x cubed, which looks like this, goes down on the left and up on the right. If you negate that and say negative x cubed, then it goes up on the left and down on the right. Right. So these are all the ones for positive coefficients. So what happens if you have a x raised to a power that is a fraction? Just as a review, let's quickly review a little bit of exponent rules. Let me do that over here so we can talk about radicals and exponents. Okay, so we know the meanings of different things, right? If I have x to the 1, that means a single x. If I have x squared, that means 2 x's are being multiplied, right? X to the 4 means 4 x's are being multiplied, right? So if you have an integer power, it literally means that many x's multiplied, right? But there's a different meaning if you have a fraction. 1/2, it means that you're taking the second root or the square root of x. If you have x to the 1/3, it's the third root of x, right? Right, and that means there's some number where you have 3 copies of it that are multiplied to produce that x, right? So for example, the cube root of 8 means what number multiplied by itself 3 times gives me an 8, which is a 2. And that's why you can have cube roots of negatives, right? You could have a cube root of -8 because, right, you could have 3 -2's multiplied together and they will produce a -8. But you can't have a square root of say -16 because there are no 2 values that would multiply that produce a negative. So you can never take square roots or fourth roots of negatives, but you can take like cube roots and fifth roots of negatives. So that's okay. Okay. So the curves look like this is the classic curve for a line, classic curve for x squared, x cubed, x to the 4th. It looks like x squared, except that the 0 is broader, it's flatter, and even flatter still for x to the 6th. So the way I think of it is, if you have this x squared, this x is a 0, and there's 2 of these zeros here. They kind of act like magnets that pull this curve down. If you have x to the 4th, there's 4 0 magnets here pulling this down, so they exert that force further out and they keep the curve closer to 0 for a longer period of the domain. Okay, well, square root is the inverse of x squared. So whenever we have an inverse function, the way you can graph an inverse function, getting pretty cluttered on this thing here. The way you can graph an inverse, let's just take the case of x squared and square root of x. Here's x, here's y. If I have the function y equals square root of x, or sorry, x squared, that has this shape right here. And remember, if you ever need to graph something and you don't have a calculator handy, you could always just pick values, plug them in, and see what you get as an output. 4, 1, 2, 0, 1, 4, and graph it that way with points. Okay, so that's y equals x squared. Okay, the function for y equals the square root of x, because square root and square undo each other, they're inverse functions, is if you were to draw a line where y and x are equal, then we're going to be essentially swapping x and y, right? If I were to swap an x and y here and make this x equals the square root of y, and then square both sides, I would get x squared equals y, which is the inverse function, right? So the graph of the square root function is the graph of the y equals x squared function, except flipped over this line y equals x. So that would look like this. Okay, now I would normally put this in here like this, right? If I just take that and swap the x and y, you would get that graph. Except that if I did that, this would fail the vertical line test. So we define it so that the square root can never produce a negative output, so that we only get the top half of that. And that is why the square root curve looks like that. Okay. It's just this arm of an x squared curve, except with the x and y reversed. And the same thing is true for a cube root. A cube root of x is just the x cubed curve, except reflected around this line. So it goes down and then up instead of up and then down. Okay, so that's how you can figure out the graphs, shapes of power functions, including their corresponding radicals. Okay, the higher the power, the flatter the curve is near zero, and the faster it goes off to infinity, as we mentioned. If you have y equals x squared, if you put 0 in, you get 0 out. If you put 1 in, you get 1 out. So they all go through the point 0, 0, and 1, 1, and negative 1, 1. Right, but the higher the power, the longer this stays close to 0 and the faster it leaves. So this is the x squared curve, x to the fourth curve, x to the sixth curve rises more rapidly. Same thing is true for the odd powers. Okay, classify each of these as power function, root function, polynomial, and so on. Okay, so let's see, this is the fifth root of x, which could be rewritten as x to the 1/5, and that makes this a power function. Okay, this one is integer powers only, so this one we can call a polynomial. And the degree would be 9. This is a 9th degree polynomial. This one is a trig function, trigonometric function, because it involves a tangent. Okay, this one is a square root, and it's got squares in here. This is more complicated, so it involves some sort of arithmetic combination of things, or algebraic combination of things, but it's not a basic curve shape of any of the original function families. So we just call this one an algebraic function. We compute it using algebraic symbols. This one qualifies as a rational function because we have a polynomial over a polynomial in the form of a fraction. That would be called a rational function. And this is a logarithmic function. Okay, so just terminology there. Without a calculator, match each equation with its graph. We have x squared, x to the 5th, x to the 8th. Well, the first thing is this is the only one that has an odd power. So that's got to be this one. This one is y equals x to the 5th. These both are even, so they both go up or down together. And the one that is moving most rapidly is going to be y to the x, or yeah, x to the 8th. So this black curve here is the x to the 8th. And this blue curve here is the x squared that's not moving as abruptly. All right. Standard form for x squared. So this is the basic form y equals x squared. But if you shift the vertex around or make it skinnier or fatter, then we call that a transformed version. And we can easily sketch that if we put this into its standard form. The standard form is y minus some k constant equals another constant a times x minus h squared, where the vertex, this location right here, is hk, and a is just some factor that we adjust. So the larger this is, the taller and skinnier this is. Okay, and if we want it to open downward, we make this a negative. So this says find the quadratic function which matches this graph. So if we know the vertex is at 6, 0, that's my hk, then I could start by saying, let's take a pattern for this. Y minus k equals a times x minus h. A lot of times we're going to be attempting to match things. So we would have to match, we'd have to figure out what those three numbers are in order to match this curve. We'll start by just filling in the fact that we know h is 0, or h is 6 and k is 0. So that means this is y minus 0 equals a times x minus 6 squared. Okay, or y equals a times x minus 6 squared, right? And that leaves us with just one other thing to find, this a. Now to find that, we have to have some other piece of information, and we do. We have the fact that it has to go through this point. That means when x is 7, y must be 2. So what we could do is we could plug 2 in for y, and we could plug 7 in for x, and then solve for the appropriate a to make that match. So 2 is equal to a times 1 squared, and so therefore a has to be 2. And now we can write our final function here. Our final function, let me get rid of this. This seems to be messing with the tablet. Okay, so that would be a is 2, so it's going to be 2 times x minus 6 squared. Here's the specific parabola that, or quadratic function that's that. Now, we could also multiply this out. Let's say that we had y equals 2. If I multiply 2 of those x minus 6's, I've got my 2. This is x times x is x squared minus 6x minus 6x, and then plus 6 times 6 is 36. If you combine like terms, you get x squared minus 12x plus 36. And then if you distribute that 2, we could also write this as y equals 2x squared minus 24x plus 72, right? That's another way to write this. So this and this are equivalent, but we don't have to do that unless the problem tells us to do that, okay? Let's make that 72. What if we were given the result? What if we were given f of x is 2x squared minus 24x plus 72, and we wanted to graph it, and we weren't allowed to use a calculator? This was on the non-calculator part of the test. Well, we could do that by completing the square. So there's a procedure called completing the square that we can employ here. And we do need this, so we definitely want to review it. Let's just use the symbol y for this. And then I'm going to do this. I'm going to bring this 72 to the other side. So I'm going to write this f as y. I'm going to subtract the 72 over to that. That's the first step. And then I know that my form that I would really like this to be in is in the form y minus h equals a times x minus, or this is k, sorry, y minus k equals a times x minus h squared. So I'd like that to be a perfect square. So I want to turn this side into something like that. All right, so let's work on that. We have y minus 72 over here, and we could factor out a 2 first. That would leave x squared minus 12x, and then I'm going to leave a little space here. And then I'm going to try to write this. So this 2 is the same, but I'm going to try to write this as a perfect square. So here's the completing the square procedure. What you're going to do is take this number here. Well, first, I'm just going to copy that this is an x. You're going to take this number here, including its sign, and divide it by 2 and produce that number here. So that's going to be minus 6. And then you're going to take that number and square it to produce a plus 36, okay? Because this and this are equivalent, okay? If you don't believe me, let's take x minus 6 and multiply it by itself twice. So that's going to be x squared minus 6x minus 6x plus 36, which produces x squared minus 12x plus 36. And now you can see why we produce this. The reason we cut this number in half here is because this number is always half of this because there's 2 of those. And then this number over here always ends up being that number times itself. So to produce this number, we take this number in the middle with its sign, divide it in 2, and then square that number and put it here. But here's the problem. If we do that, now we've disturbed this equation. This is no longer equal because we added this right in here. What we really did is added a 36 times 2. We effectively added 72 on this side, right? So that means we have to keep it balanced by adding a negative 70, or adding a 72 on this side as well to balance it. So to balance the 72 we added over here, we have to add a 72 here. And that means that our new left side is y minus 72 plus 72, which happens to be y plus 0. Okay, so then this is just y plus 0 equals 2 times x minus 6 squared. And then we could graph that by saying, okay, the vertex is at x is 6, y is 0. So I know we're here at x is 6, 0. I know there's a vertex, and this is positive, and this opens upward. And then we could say, well, normally we would graph a regular shape X, but this is twice as narrow. So we know it looks roughly like that. So even without a calculator, we could get a rough idea of what this is. Okay. So completing the square, an important procedure that we need to be able to convert polynomials into standard forms. Okay, graph by hand each of these and notice the relationship between the following graphs. Okay, so if I want to graph 2 to the x, I'm just going to graph these by making little tables if I have to graph by hand. So if I put 0 in here, 2 to the 0 is 1, right? So 2 to the 0 is 1, that's this. If I put 1 in here, I have 2 to the 1, which is 2. If I put 2 in here, I have 2 to the 2, which is 4. And let's try a negative number, -1. That's 2 to the -1, which exponent property means you move it to the other side of the fraction, make it positive, which is 1/2. So this has this characteristic shape. This is a power function, or sorry, exponential function. And it has an asymptote here. It approaches 0, and up here it goes off to infinity. So that's the graph of 2 to the x. Okay, let's take a look at 1/2 to the x. What would that look like? Okay, so if we take 0, that would be 0.5. So that's 1/2 to the 0 power, which is 1. If I put a 1 here, it's 1/2 to the 1 power, which is 1/2. So at 1, this is 1/2. And if I put a -1 in, I'm going to have 1/2 to the -1, which is equivalent to flipping this upside down to the +1, which is 2. So -1 is 2, and in fact, this produces this graph. So this is the graph 0.5, or 1/2 to the x power. 1/2 to the x power looks like exponential decay. 2 to the x power is 2 to the x. Okay, let's do a graph for this one. I'll put it over here. If we have x and 2 to the -x, what does that look like? Okay, so if I put 0 and 2 to the -0 is just 2 to the 0, which is 1. If I put a 1 here, it's 2 to the -1 power, which is the same as 1 over 2 to the positive, so that is 1/2. If I put a -1 here, it's 2 to the -1, so that's +1, which is 2. So this is replicating this graph. This graph also comes about if I have 2 to the -x. So you get exponential decay here if you have a positive, or you have a base greater than 1 and you're raising it to a negative power, or if you have a base that's less than 1 raised to a positive power. If you have a base that's greater than 1 raised to a positive x, then you get exponential growth. Okay, and this last one is 4 to the x. So if I put a 0 in here, 4 to the 0 is 4. I'm sorry, 4 to the 0, anything to the 0 is 1. Sorry, that's 1. So that goes through that same point. They always go through this point 0, 1. This would be 4 to the 1, which is 4. If I put a -1 in here, it's 4 to the -1, which is 1 over 4, which is 1/4. And so this is also exponential growth, but more rapidly. So 4 to the x grows more rapidly and also goes off to 0 more rapidly. Okay, so some things to know about the way power or exponential functions behave, right? The larger the base, the faster it moves, right? If you have a positive, or a number greater than 1 raised to a positive x, it's exponential growth. If you have a fractional power raised to a positive x, it's exponential decay. If you have a base greater than 1 raised to a negative, it's also exponential decay. Okay, knowing, let's see, for each scatter plot, decide what type of function you might choose as a model. Well, this is periodic, which means I think we should use some form of trigonometric function. Trigonometric function. Maybe a sine wave shifted up. If I had to guess, it would be, let's say, for example, this is 3, and then we go from 4 to 2. Maybe I could say the amplitude of this is 1. And then we're going to use a sine wave for something. I'm not going to worry about all this. Let's just say x, and then we'll just shift it up by 3. So if we do something like that, a sine function is going to be able to model that. This appears to be linear. So we just need a linear function, maybe something on the order of, I don't know, if this was, let's say this was 50 and we went down with a slope of, we went down 2 for every one that was over. So maybe we would do negative 2x plus 50, something like that. So sometimes you can use a graph to kind of match points like that. Okay, for this last problem in the notes, we're going to do various things to try to fit a line to a set of data. We don't do this frequently in the class, but it does come up here and there. Let's say we had income in dollars and we had the ulcer rates per 100 people. This is really old data, so the income numbers are really low. And to make the numbers a little more manageable, I'm going to take the income and write it in thousands of dollars. So 4, 6, 8, up to 60 here, which means we have data points. Like this first data point is X is 4, Y is 14.1, and this last data point is 60 for X and 8.2 for Y. Okay, this says make a scatter plot, decide whether or not a linear model is appropriate. Now we reviewed this on the first day, but if you take data and enter it into lists, so you say stat, edit, and you enter X's here and Y's here. Then you can go into second Y equals, turn on a statistics plot, set it to be a scatter plot. And then let's see, let me get rid of this here. Let me get rid of these. Okay. And then what you can do is say zoom 9 to display it and see the shape of the data, which does indeed look linear. So it is appropriate for me to use a line to model this data. And then can we find and graph a linear model using just the first and last data point? So instead of trying to fit a line to the whole data point, can I just use the 2 endpoints? Okay, to do that, what we're going to do is just come up with a template. Y minus Y0 equals mx minus x0. And we have to figure out a point on that, which I'm going to use 4 and 14. So this will be y minus 14.1 equals some slope times x minus 4. But for the slope, we'll use the slope formula that you use the change in y minus the change in x. Okay, so the change in y here is, if we go from here to here, I'm going to make this the end. So let's do 8.2 minus 14.1 over 60 minus 4. And that turns out to be, let's see, 8.2 minus 14.1 divided by 60 minus 4 turns out to be negative 105,357. 105,357. Rounding it to quite a few decimal points there. Okay, which means I could write this as y minus 14.1 is equal to negative 0.105357 times x minus 4. If I multiply this out, I get negative 0.105357x. And then if I multiply that times 4, oh, it's times negative 4, times negative 4. I get that this is positive 0.42143 about. And so then if I add the 14.1 to the other side, I get negative 0.10536. I'll just abbreviate it there. And then this number, let's see, that should be plus this, right? Yeah, plus. And then I'm going to add on 14.1. Okay, so we've got plus 14.52 about. 0.5214. Okay, so here is an equation that we have fit just to the last 2 data points, okay? And that's the answer to part B. Find a line that matches the 2 data points. So whenever we're asked to find, to fit a function curve with some constants, we can just force it to go through different points. In this case, if it's a line, you can find the slope by using the slope formula and then plug in one of the endpoints. Okay, in this next part, it says find and graph the least squares regression line, which means to this means to use the calculator's regression features to fit a line to that. So for this one, we can run linear regression by going stat over here to calculations, linear regression number 4, list 1, list 2, and let's put the result in y1. So their slope is negative 0.0998. So negative 0.0998 times x, and their y-intercept constant is 13.951 approximately, plus 13.951. A little bit different than what we got when we fit the line to just the endpoints. So if we actually look on the screen here and I do zoom 9 to redisplay that scatter plot, it shows that line that the calculator came up with, and you see that it's not going through the two endpoints, it's going through a mix of all the points, which is what regression does, tries to minimize the error overall. But if I manually enter in y2, let's enter the line we calculated by hand, which is negative 0.10536x plus 14.5814, and then I redisplay this. There's the line of best fit, but here's the line we came up with that just specifically goes through the endpoints. So if you just use 2 points, you're going to get something that's accurate for those 2 points, but not for the entire data set necessarily, which is why regression is kind of nice. All right, now that we have that, it says use the linear model in part C, which is the regression one, to estimate the ulcer rate for an income of 25,000. So once we have a model, that means we can plug in an X and find a Y, or a Y and find an X. So if they want us an ulcer rate for 25,000, that's equivalent to having, so for part D, having X equals 25. So I'm just going to use the linear regression model, 0.0998, but plug in 25, 13.951, to get the answer, which turns out to be 11.456. We should always report to 3 decimal places and put units. This would be ulcers per 100 people. Okay, and the other symbol we can use for that is F of 25. All right, next it says, according to the model, how likely is somebody with an income of 80,000 to suffer from peptic ulcers? So that's just giving me a different X value. So I'll evaluate F at 80. And when you plug that in, you get negative 0.0998 times 80 plus 13.951, and we get 5.968 ulcers per 100 people. Okay. Do you think it would be reasonable to apply this model with somebody for an income of $200,000? So should we do this? Should we do F of 200? Well, I mean, algebraically we can. If we do that, we end up getting negative 6.006. So we definitely can't have negative numbers. So the answer to that question is no. That does not produce a reasonable answer. And the reason for that is if we look at the model kind of indicates that if you go to enough income, eventually you're going to get to a negative number of ulcers. So this in real life would definitely have to level out and be nonlinear at some point. So one thing about models is that they're really only valid over the region of the domain for which they were developed. You really can't use them very far past the points. In AP statistics, we call that extrapolation, and there's a hard, fast rule that you're not allowed to use a model anywhere outside of the region where it was developed. All right, so that should wrap up that video, and that should hopefully give you enough to be able to do homework problems.